Hi, Brian Miller-Hicks, a continuing series of narrated PowerPoints in Earth Science. Today we're talking about metamorphic rocks. Metamorphic means, if you translate it from the original Greek, I believe, meta means change and morphic means shape. So a metamorphic rock is a rock which is changed in shape through the factors of increased heat, increased pressure, time, of course, which is the framework for all geologic processes, and to a secondary degree, fluid in pores of rocks between crystals and minerals, mostly in the form of water. So behind me is a photo I took in Palm Canyon, Deep Canyon in the Palm Desert area. It is an outcrop or exposure of metamorphic rocks. And you can see another viewpoint of these same metamorphic rocks in my title slide. You can see my friend Dr. Monty Marshall here standing at the base of this cliff, which exposes metamorphic rocks which have been changed through heat, pressure, time, have been deformed plastically. That is a key. Metamorphic rocks deform plastically because typically those conditions of heat and pressure which change rocks occur deep down below the surface of the earth. If you follow my laser pointer here, you can see these bands or layers of rock, and they go this way, then they come back this way. This is called a Z-fold. So these are rocks that were originally horizontal strata, which have been deformed by pressure and heat and folded, just like you fold a piece of paper, sheet of paper, folded into this Z shape. This takes a tremendous amount of pressure, temperatures between 150 degrees centigrade and 800 degrees centigrade, and time. Now, anything above 800 degrees centigrade, rocks start to melt, and then they become, as you know, igneous rocks. So let us proceed. Again, you've seen this before. This is, of course, the rock cycle again. And we're looking at this part of the rock cycle that deals in metamorphic rock. Sedimentary rock transforms through heat and pressure. If it's buried deep in the crust, heat and pressure cause it to become metamorphic rock. If metamorphic rock melts, it of course becomes igneous rock. Okay. Now, when we talk about the forces that act on this rock, we talk about pressure, stress, and strain. Pressure is also called stress. Here we see a depiction of what we call confining pressure, excuse me, which means that pressure on all sides is equal. So pressure here is the same as pressure here, is the same as pressure here. Another example of confining pressure would be if you were a scuba diver and you dove into the ocean 20, 30, 40 feet down, you would have equal water pressure all around you. The reason why you don't become deformed is because the internal pressure in the fluids and air within your body counteract the confining pressure around you, although you do feel that sensation of increased pressure. So with confining pressure, you have layers of rock that are buried, but even if they're buried fairly deep, if the pressure is the same all around, they tend to be undeformed. Now, what happens if you have more pressure in one direction than another direction? This is a tectonic scenario where you have a continental plate here colliding with another continental plate. This, as you know, is a phenomenon of a convergent tectonic boundary, convergent collision zone. Now you have more pressure in this direction in this direction than you have in this direction. So as a consequence of this differential pressure or differential stress, the strata then become deformed. Now the strata, which was originally horizontal uniform layers, tends to fold into these folds as you see here because of the differential stress. Undeformed up here, so shallow burial here, no differential stress. When you get into the central core of the mountain range, as these two plates are squeezing against each other, it sets up differential stress or pressure and deforms the rock at certain depths. The deeper you go, the warmer it gets, the more stress there is, you tend to see more deformed rocks. So if you take a trip across these beautiful United States, you cross Rocky Mountains, you cross the Appalachians, you look at the road cuts, you'll see some of these folded, deformed, stressed layers that have been caught in the vise of tectonics. You see other scenarios that cause metamorphism. So let's start here. Deeply buried sedimentary strata are metamorphosed, uniform stress, but they can still be squeezed down and compacted by weight of layers above them in a subsiding basin. So sediments tend to collect in basins, and as they get buried deeper and deeper, they become more and more compacted, cemented, and turn into sedimentary rock, or mildly metamorphosed if there's enough pressure. Here you have what we call contact metamorphism. It's called contact metamorphism, which you see occurring around the borders or the boundaries of igneous bodies. Igneous bodies, of course, are molten rock or magma, which is very hot, and the very hot molten rock tends to metamorphose the pre-existing rock around it. So if this magma, for example, is rising through the country rock, it will bake, transform via heat the rock around it. That's thermal metamorphism or contact metamorphism. You also have metamorphism through subduction. You have this mechanism of a plate subducting underneath another plate. As it does so, the sediments that were originally on a flat seafloor are now being squeezed by being rolled under this continent, being subjected to increasing pressure and increasing heat, and thus metamorphosing. You see this temperature gradient here ranging from 300 to 1200 degrees centigrade. Of course, down here it's molten rock. Up in through here between 300 to 800, it's still metamorphosed, it's not quite melted. Okay. Now, geologists recognize grades of metamorphism: low grade, medium grade, high grade, or low grade, intermediate grade, and high grade. It has to do with temperature and pressure. Once again, at 200 degrees centigrade, you have low grade metamorphism. You tend to get metamorphic type minerals like chlorite, which is sort of a transformed clay mineral. Intermediate grade, higher temperature, higher pressure, you get muscovite, biotite. And then as you get into the real high grade, higher temperatures, higher metamorphism, you get very unique special minerals called, for example, staurolite or sillimanite. Now, it's important to recognize that through metamorphism, rocks can change in texture, can change in density, can change in color, can change crystal or mineral makeup. A metamorphosed granite, for example, can have completely different or new minerals that are formed only under metamorphic conditions. So a mineral like garnet, a mineral like sillimanite, or a mineral like diamond even forms only under metamorphic conditions of higher temperatures and higher pressures. Down here in this graphic, you see a bar which depicts the change of rock type through metamorphism. If you start with it doesn't say here, but let's say you start with a shale or a mudstone. Through increasing metamorphism, that shale will then change into a slate, and then into a phyllite, then into a schist, into a gneiss, that's pronounced nice. Okay, so each one of these rocks, slate, phyllite, schist, and gneiss, is a distinct, different rock with different texture, different grains, different structures, and even different minerals in it. The slide's a little complicated, but let me lead you through it. So again, we start with shale or mudstone, low-grade metamorphism, through intermediate metamorphism. As this rock starts to get squeezed through differential stress, it actually starts to get folded under ductile conditions, which means under conditions where rock, instead of breaking and fracturing, it actually flows, and slowly, although, of course. Under those high conditions of pressure, it acts more like a putty, which is bendable and foldable, rather than a brittle rock. So the rock starts to fold, and as it does so, it develops secondary planes, like you see running up through here, which are the axes of these folds. So we get bedding planes that develop like so, which become more and more prominent. So you see these bedding planes showing up here, showing up here. The squeezing is still side to side, but it actually forms secondary planes that go up and down, like you see here. So if you get uniform, regular planes like this that go vertically up and down, you get perhaps something like slate, which forms into very flat, uniform plates of rock, plates of slate. This is a quarry where they mine slate, which turns out to actually be a very useful building material. What can you use slate for? Sidewalks, patios, decks, swimming pool decks, pool tables. Okay, slate is very useful because it's dense, it's tough, it's durable, it's flat, and it's plated. People in other parts of the world use slate on their roofs. This is hand-cut, hand-shaped slate formed into tiles that form the top of this house, this roof. Now, slate's heavy. It's a rock, so you want to make sure your beams are strong, your joists are strong, and your foundations are deep and strong. Here's another type of metamorphic rock called a schist. Remember, a schist is fairly high-grade metamorphic rock, and it's a shiny piece of rock because what you see here are hundreds or thousands of flakes of mica, which, as you recall from learning about minerals, is a flat sheet-like mineral which reflects light. It's silicate. This is another type of schist, and here's another type of metamorphic mineral. These lovely purplish red mineral crystals are crystals of garnet, which is used in jewelry. Often gemstones, jewelry, stones we use in jewelry are durable, tough, metamorphic minerals, like garnet. A gneiss is a transformed rock, transformed by metamorphism into, it can start as granite, or it can start as a shale, and it's got a characteristic stripy pattern. That's called foliation, F-O-L-I-A-T-I-O-N. It's a distinct texture that you'll find only in certain metamorphic rocks. So let's look at, we've talked about the large scale processes of metamorphism. Let's talk about sort of the microscopic scale of metamorphic processes that have to do with individual mineral grains, stress, heat, and fluid, water primarily, in the rock itself. Rocks do contain water. Magma contains water. Sedimentary rocks can contain water. So before metamorphism, we have uniform stress. We have a piece of granite here. We squeeze and heat up this rock, metamorphize it, if you will, through differential stress. And now these individual black mineral crystals start lining up perpendicular to the direction of maximum stress. So there's the maximum stress left and right, and they start lining up vertical or near vertical. This gives you the characteristic pattern that we know as foliation. Again, on a microscopic scale, a number of things happen to individual crystal grains. So if you look at a piece of sandstone, which has primarily made of quartz, you start metamorphosing it, the grains start deforming at a microscopic scale by the slippage of crystalline planes. Okay, the original shape of the crystal is this dashed line, and as you apply differential stress, the grain starts to flatten and lengthen. Grain is distorted as ions move from more stress to less stress sites. Well, what does that mean? Well, that means that when you apply pressure to this rock, it releases or peels off ions in this stressed area and adds them to this less stressed area here, so that ions are removed from here and migrate, being carried by water, to the ends where they redeposit, if you will, on this end and this end. That gives the grain its flattened shape or distorted shape. Here's a conglomerate, which you know is a sedimentary rock that you might find from a cemented, buried, and compacted river channel or gravel bar. And as you can see here, the grains or the cobbles within the conglomerate have been squashed, flattened, and lengthened. Now, there are foliated metamorphic rocks that I've already discussed, and there are non-foliated metamorphic rocks. Non-foliated means you don't see the stripy mineral pattern. Okay? An example of that is marble. Marble starts out as limestone. Through metamorphism, it becomes marble. The calcite, calcium carbonate crystals in limestone, in this case, actually grow larger. The smaller calcite grains in limestone start dissolving and then redepositing themselves as larger grains. And that's what you see in a nice piece of pink marble. On a microscopic scale, this is what marble looks like. Each of these areas here is a crystal or a grain of calcium carbonate packed together. Marble, of course, is useful to us as a building stone. We use it in decks, we use it in buildings. We also use it in art, of course. This is the famous statue of David by Michelangelo. Actually, it's a replica of the statue that stands outside a building in the city of Florence, Italy. And here's another non-foliated metamorphic type rock called a quartzite, composed primarily, of course, of quartz. Thank you.